After it is designed, but before it can be occupied, a building must be constructed. This is the story of the construction of Milstein Hall at Cornell University. The heart of Milstein Hall is the upper-level floor plate devoted almost entirely to the architecture department's design studios. Unlike the concrete lower-level slabs at the first floor and basement, or the concrete dome, the second-floor studio spaces are contained within and supported by a steel frame. The construction of this steel superstructure was described in a prior video in this series. To quickly review the process, steel beams, girders, and rigid frame trusses are put in place. Then corrugated steel decking is welded to and made to span between the beams. Welded steel plates are fastened to the steel beams to form vertical edges to the corrugated slab. Otherwise, the concrete cast on top of the deck would not be contained. Notice that there is a substantial gap between the edge of the Milstein slab and the wall of the existing building in order to allow for movement. Shear studs are welded to the girders and beams through the steel deck so that these steel beams become integral with and can act compositely with the concrete deck. In other words, the concrete above the beams becomes part of the beam or girder profile, increasing its strength in bending and its resistance to deflection. While the steel floor structure is for the most part hidden by the building's cladding and soffit material, it is not entirely forgotten. Glass fascia panels at the rectangular floor opening for the stair reveal these girders, beams, and bolts in all their utilitarian and pragmatic glory. Even ordinary construction details get their 15 minutes of fame. Unfortunately, these open glass panels can also trap moths and other creatures, potentially turning this exhibition of structure into an entomological display case. This floor also functions as a radiant slab for heating during cold weather. For this reason, PEX tubing, made from cross-linked high-density polyethylene, or HDPE, that is melted and then continuously extruded, is used to bring heated water into the slab. It is placed over the metal deck and will be embedded within the concrete. These tubes terminate in manifolds that are accessible through steel doors built into the future concrete slab. Here we see the access panel box from the bottom, looking up from the first floor. Electric conduits, floor-mounted electrical outlets, and hard-wired data cables are also placed over the metal deck. Once all these electrical and mechanical elements are properly positioned, concrete is cast over the metal deck in alternating bands defined by temporary wooden edge forms that are aligned at the precise height of the structural slab. The first batch of alternating concrete bands are cast. Once they harden sufficiently, the wooden forms are removed and the edges of the hardened concrete serve as forms for the remaining bands. Looking through the window from Sibley Hall, we can see the concrete being pumped onto the second floor and manually spread over the steel deck. A temporary vapor barrier is placed over the concrete to prevent evaporation of water as the concrete cures. The access doors for radiant heating, as well as floor-mounted electric boxes, are a bit higher than the structural slab since they align with a topping slab not yet cast. The steel deck serves not only as formwork for the concrete, but also as tension reinforcement. In other words, neither the concrete or steel by itself could adequately support the anticipated floor loads. However, the interaction of the two materials creates what is essentially a reinforced concrete slab, with the steel deck taking the place of reinforcing bars. Steel welded wire mesh is put in place for the lightweight topping slab, as it was placed in the structural slab below to prevent cracking due to concrete shrinkage. This topping forms the final and finished floor surface for the studio floors. The surface is finished with a power trowel and will eventually be waxed once all the construction on that level is completed. A more specialized topping product, Ardex K15, is placed into the access panels for the radiant heating tubes so that the floor surface seems more continuous. The space between the concrete slab and steel curtain wall framing is filled with a gray sealant. The topping slab, while reinforced, has no control joints, and it has experienced extensive cracking, especially at sharp corners. One area of the floor plan, designed as a kind of lounge area, will be finished with a wood floor. The wide planks of ash are screwed into 2 layers of plywood, which act much like the subfloor in conventional wood-framed construction. To allow for expansion and contraction, the space between the wood and concrete finished surfaces is filled with cork. As often happens when very wide planks are used, the wood exhibits considerable cupping, as can be seen here. This area aligns with a stainless steel covered electrical closet and a small sloped seating area directly over the dome below. The sloped seating area facing this projection screen is first cast as a simple inclined slab on its steel frame. The actual seating is formed with wood, and the edge is lined with aluminum panels. Later, an aluminum gridded egg crate guardrail is screwed into place. An aluminum plate welded to the aluminum egg crate is bolted to a steel plate that has been welded to the steel structure of the inclined plane. A similarly exposed system of bolted plates is used to attach handrails to the inside plane of the aluminum grid. Unfortunately, this aluminum gridded guardrail didn't really work that well. It was a bit too flexible, and so it was removed during the 2012 winter intersession and replaced with a welded steel version, painted white. This steel frame, temporarily held in place with clamps, will be welded to the same steel plate to which the aluminum structure was previously bolted. Then, painted steel gridded panels will be bolted into these steel posts. Diagonal struts that maintain the desired geometry of the steel frame are cut off once the frame is in place. The gridded panels are lifted into position and bolted into place. Sometimes the holes need to be enlarged so that the bolts can be made to fit properly. Once the panels and posts are aligned and fitted, the posts are welded in place. The old aluminum handrail is then bolted in place, and, after a bit of touch-up paint, the new guards are complete. The electrical closet is constructed with metal studs and plywood sheathing. Then, polished stainless steel panels are glued to the sheathing. Doors facing the sloped seating area can be opened to create a projection screen. This screen faces the sloped seating.
What does it take to understand? Learn the music, join the band. Give me your hand to shake.
Aluminum panels are fastened to the inclined steel structure, and glass walls and doors provide acoustical separation from the auditorium below. At the time of this filming, the joints where the aluminum panels intersect seem a bit sloppy. This detail is on a so-called punch list, that is, a list of items not meeting the requirements of the drawings and specifications that will be fixed by the contractors once students leave for intersession. Here we see the corrected detail, a bit better than before, but still not perfect. Stamped aluminum panels, resembling a 19th century tin ceiling on steroids, form the underside of the sloped plane, matching the ceiling treatment on the auditorium below and the rest of the first floor soffit. Glass guardrails set into aluminum channels protect the openings around the entrance stair, with plywood standing in temporarily for some missing glass. Here we can see the installation of curved and sloping glass guards for the stair leading up to the studio floor. Temporary wooden shims are used to align the glass panels within the aluminum channels. Other ad hoc methods are also employed for this purpose. While ordinary shims and gaskets are used for the standard straight glass guards, the curved ones require a more handmade approach. After a backer rod is inserted into the floor-mounted channel and the glass is pushed into place using scraps of wood, an anchoring cement is mixed and then poured into the floor-mounted channel to secure the glass. Then, the aluminum channel cap is painstakingly cut, ground, and bent by hand until it fits the curve of the glass. A black sealant is used instead of the standard black gasket, and an aluminum strip and gray sealant finishes the job. Another type of guardrail shows up under the sloping truss diagonals, necessary and required by code so that building users don't hit their heads on the angled steel truss sections. Because Milstein Hall is meant to connect East Sibley and Rand halls on their second floor levels, openings must be made through the masonry walls and windows of these two existing buildings. Here we can see the opening being made in Rand Hall. Because it is a steel-framed building, the thick brick cladding can be removed without compromising the building's structure. Both a glass wall protected by a horizontally rolling fire shutter and a 1-hour fire-rated glass door are then installed. At Sibley, an older structure with load-bearing brick walls, two strategies are employed. Mostly, a series of small openings are made by removing brick below existing windows. This minimizes structural disruption to the wall since the windows are already spanned by brick arches. New glass doors with 1-hour fire resistance ratings are placed in these openings. At the end of Sibley, a more difficult opening is made in the brick wall. Temporary shoring supports a new, larger opening until a steel lintel can be inserted. After all this effort, it is a bit surprising to see the result. A small steel door is installed within a steel stud gypsum board wall. I've been told that the double-wide glass door that was originally envisioned proved to be too costly and so was replaced with this lower-cost design. To create a 1-hour fire barrier between Sibley and Milstein Halls, the existing windows that are not extended into doors are covered not with 1-hour fire-resistive material, but with 3/4-hour fire-rated glass in a metal frame that is screwed into the existing wooden window frame. Here we see fire-safing material inserted into the space between the glass frame and masonry walls to ensure the continuity of the fire barrier. This fire-safing is then covered with a sealant. Finally, the new fire-rated glass is cleaned. That's pretty much it on this floor level. The ceiling is just the exposed structure and skylights, along with electrical lighting, pipes for chilled beams and sprinklers, and some ducts for fresh air. A mock-up of the lighting is shown here, fastened to the same unistrut channels that will support chilled beam units. The chilled beams and their pipes for cold water can be seen here, along with lighting fixtures that are the same size and shape as the chilled beams. There are also insulated roof drain pipes running exposed through the second-floor space. Ductwork brings in dehumidified makeup air that is tempered in both summer and winter from a mechanical room on the 3rd floor of Rand Hall. Return air is brought back from Milstein into Rand, as can be seen in this sectional view, which also shows the supply ducts coming down at the ceiling level of Milstein and then working their way through holes in the steel framing of Milstein Hall in order to provide fresh air throughout the studio space. With this plan, none of the ducts need to actually penetrate through the open studio floor, with one exception. A toilet exhaust duct from the lowest level needs to work its way up through the building somehow. A space for this duct was found adjacent to the elevator shaft. Electricity and data are brought to the workstations in 2 ways. Data and power are supplied from floor-mounted boxes that were embedded in the concrete slab. More power is available from electrified tracks suspended from the ceiling into which wires can be plugged. There are also wireless access points mounted in the ceiling. The structure and mechanical electrical systems are entirely exposed, except that acoustical panels have been fastened to the underside of the exposed metal corrugated roof deck to make the space less reverberant and to attenuate noise. There needs to be a substantial space between the new and existing construction, since the structural frame of Milstein Hall is designed to be entirely separate from the structure of the existing buildings, and sizable differential movement could occur as a result of wind or earthquake loads. At the floor level, these building separation joints, sometimes called expansion joints, consist of bent aluminum plates pictured here at the intersection of Milstein and Sibley Halls, with AAP Dean Kent Kleinman also visible through the south windows. These bent plates are fastened to the existing building walls only, covering the void while allowing lateral movement between the slab and wall. Aluminum saddles at the numerous connecting doors are cut to align with those angles. At the ceiling level, horizontal framing studs are hung from the structural slab to support aluminum panels, forming a soffit that covers the somewhat messy condition above, in this case accommodating a continuous gutter below the level of the roof deck designed to collect water not absorbed by the green roof. Vertical building separation joints are also needed between Milstein Hall and the existing buildings it connects to at this level, in this case East Sibley Hall. Typical proprietary seismic joint details consist of rubberized bellows that can expand or contract as the two buildings move during a seismic or wind event. Here we see the bellows installed between Milstein and Sibley Hall at the southern facade. The New York City-based design firm 2x4 Incorporated was hired to create a signage system for Milstein Hall. They used cutout letters and figures that are adhered directly to the concrete slab. First, an adhesive primer is applied to the concrete. Then cut-out thermoplastic letters and figures are placed over this adhesive. Finally, the whole thing is made permanent with a blowtorch.
Carry out 90 o'clock in front of this fire.
Green letters are used at the entrances to the space being labeled, while white letters with arrows are used to point you in the right direction. The last elements that define the studio level are curtains that provide some protection from the east, west, and southern sun. These curtains, designed by Petra Blaze and her firm Inside Outside, are hung from tracks mounted to the ceiling structure. The curtains, when drawn, obscure the steel rigid frame trusses, so a decision must be made whether to place them on the outside of the trusses so that the trusses remain visible from the inside, or on the inside of the trusses so that the trusses remain visible from the outside. As it turns out, both strategies are used. The western facade curtain tracks are placed between the curtain wall and the trusses, leaving the steel frames visible from the inside but not from the outside, while the eastern curtains are moved further inboard so that the trusses, while obscured from the inside, remain visible when viewed from the outside. Why would only these eastern curtains be placed inside the trusses? A seemingly irrational choice, since it effectively reduces the amount of available floor space while inviting all sorts of forbidden activity. In fact, the explanation has two parts. The first part is a site strategy that embraces the metaphor used by Cornell in its original competition brief, that Milstein Hall be designed as a gateway to the campus. In other words, the view of and approach to the building from North Campus is acknowledged as being more significant. The second part is best understood as a relic of architecture's male-dominated modernist legacy and the stereotypical gender roles that were traditionally assigned to the various building elements. So when we approach Milstein Hall from this prioritized vantage point, this gateway from North Campus, the trusses with their hyper-extended cantilevers are brought to the foreground in a classic display of heroic and masculine posturing, while the curtains, assuming the traditional role of the feminine and domestic, are pushed into the background.